All right, so today we're going to talk about the substantial derivative, and I'm recording this video at home, so the giggles you hear are my family.
Sorry.
All right, they've left. So this is going to be a quick video about something called the substantial derivative, which we're going to see a lot as we move forward. And so the substantial derivative is important when we're talking about velocities and anything that is got a vector definition that also varies in x, y, z, and t. So here, like, we have velocity, and we think about that as having an x, y, and z component, and each one of those can vary in the, each one of those components can vary in the x, y, z, and t. And so if we think about taking the derivative, say we wanted acceleration, right, which is the derivative of velocity as a function of time, right, and it's a partial derivative, then we could really think about this as being three derivatives using the additive rule, all right, and it would look like this. Let me get that j hat in there. All right, and so that's really, if we were thinking about the acceleration of this velocity vector, again, that's what it would look like. Now, the problem is if we just think about this term, let's call this ax, okay, the acceleration in the x direction, all right, we have this derivative here, d, and it would be u of x, y, z, and t, dt, and now the problem is, for instance, our positions and things can change with time, and so we really need to think about this in terms of a more complicated derivative, right? Because we could be thinking about where are we as a function of position of time. So we could think about that this x, y, and z, right, is really a position vector as a function of time, right? And so really then what we have is a sort of a more complicated term here. And so what we think is that if we think about du dt, we could think about it being du dt, that term, plus du dx times dx dt. So essentially, there's this term here, which is really sort of a chain rule here, where we're thinking about the derivative of u in terms of t, but there's this x, which is a function of t. And of course, then, that means that there's du dy dt plus du dz dt. All right, each one of these is this chain rule because our position vector can be a function of time. And if we think about that a little bit more, well, dx dt is really just what? It's really just u, right? It's the velocity. Du dx plus v du dy plus w du dz. So when we think about this acceleration term, even just in the x direction, okay, we get this very much more complicated acceleration because position can change as a function of time, right? Now we can write this in a little bit more simple way. We can write this as du dt plus the velocity vector v dot the gradient of u, and remember the gradient is a vector that is equal to d dxi plus d dy j plus d dzk. And this term here, this v dot something, all right, is really important. Now this particular form of a derivative is something we see a lot when we have these sort of multivariable problems, all right? And when we think about this first bit here is what we call the local acceleration. So this is if I'm at a position x, y, z, and the velocity is changing at that position as a function of time, okay, then this term tells me the local change in acceleration. This term, which I'll circle both versions of it up here, is sometimes called the convective acceleration. And what this term is telling us is the acceleration change as a function of position. All right, meaning that if I move from one spot to another because of my velocity, and the velocity is changing as a function of position, right? So I move because of my velocity, and the velocity is changing as a function of position. That's akin to feeling an acceleration. And the best example I have of this is to think about the idea of walking in the airport and stepping onto a people mover, and you're feeling that acceleration. You feel a force under your feet pull you forward. That's convective acceleration. It's not because you're speeding up. It's because the velocity underneath you is changing, and so you feel this change in velocity due to a velocity gradient. All right. Now this particular derivative here, this whole form of it, is so important that it's got its own name, the substantial derivative or the substantive derivative. It's sometimes called the total derivative. All right, and sometimes it's called the material derivative because it matters a lot in material properties. And so if you see a derivative written like this, capital D, capital T, of anything, then it's saying it's this special derivative. And we are going to see it, all right? We are going to see it a lot as we move forward.